Okay, so now let's continue with the three examples that we drew before. Our goal now is to define the marginal distribution of x and the conditional distribution of x given y. And again, these are I'm just trying to recall something that we have seen in the last lectures. Okay, so generally speaking, what is the marginal distribution of x? So let's define that for now. So the marginal distribution so this is simply the distribution of one of the random variables. Okay, so it's just the distribution of one of the random variables. Okay, and in this case, let's say I'm interested in x. Okay, what does that mean? So this just means that you, in some sense, you do not care about y. Okay, so let's see what that means in the discrete case, right? So in the discrete case, you just have the random variables and you have x out here and y out here. Let's take a very simple example where maybe x takes two values 0 and 1, y also takes two values 0 and 1, and let's say the probability values here are 1/2, 1/6, 1/6 and 1/6. Okay. So note that these values all add up to 1 because these three add up to 1/2, and so the total is 1. Okay. So this let's take this simple example of jointly distributed random variables x, y. Okay. So in this case, so suppose I ask you only focus on the values of x. I don't care about y, right? So this is don't care. And I ask you okay, and I ask you what is the probability that x equals 0, what is the probability that x equals 1. Okay. In this case, the way to do it is to simply say the probability that x equals 0 is 1/2 plus 1/6, because x equals 0, y equals 0 is half, x equals 0, y equals 1 is 1/6. Okay, so that's exactly what you have, and in this case, so the probability that x equals 0 is half plus 1/6, which turns out to be, I think, 2/3, and the probability that x equals 1 is 1/3. So this is a probability distribution only involving x. Okay, and this is called the marginal distribution of x. Okay, the reason it's called marginal is because if you view this as a matrix, then you could imagine writing out the row sums in the margin, and that's how it gets the name. Okay, and if you have continuous variables x, y, then you do exactly the same, right? So do the same as before. But now instead of summation, you've got to do integration. Okay, so let's write this marginal distribution as px. Okay, and if I want to define px of s, this is exactly the same as integral over all possible values of y. I will call that t. So t equals minus infinity to infinity of p x y of s comma t dt. Okay. So this is the analog of summing over t, same as t. The p x y s t values. Okay, and this is how we define the marginal distribution of x. Okay, so this is now this is called the marginal distribution of x. All right. Okay, so this is quite different from the second thing that we are interested in, which is called the conditional distribution of x given y. Okay, so what is this quantity, right? So again, let's go back to the same example of the discrete random variable. Right? So suppose now I give you a value of y, so let's say y equals 0, and I ask you what is the distribution of x given that y equals 0. So this is y equals 0, and what is the distribution of x given y equals 0. Okay. You know that now in this, at least let me redraw this example. So here, conditioned on y equals 0, this x was taking value 0 with probability half, and x was taking value 1 with probability 1/6. Okay. And here there was y equals 1, and this was 1/6, this was 1/6. Okay. And so we are interested in this column, right? So we are interested in the first column, right? And so you might be tempted to say that, oh, conditioned on y equals 0, probability that x equals 0 is equal to half, and probability that x equals 1 equals 1/6. Okay. But this is not really a distribution, right? So this is incorrect. This is not a distribution. Because a distribution is one where the values of the probability values must add up to 1. So what do? You simply normalize. Okay, so the way to fix this is normalize by the total. Total sum of the entries in the column. Okay, and that's it. Okay, so in this case, the real probability of x equals 0 conditioned on y equals 0 would be half divided by half plus 1/6, and this is exactly equal to half divided by 2/3, which turns out to be 3/4, and probability that x equals 1 conditioned on y equals 0, this is 1/6 divided by the same half plus 1/6, which is 2/3, and this would turn out to be 1/4. Okay. Note that you didn't really have to do the second calculation because you knew that the first one was 3/4, the second had to be 1/4 because the two of them add up to 1. Okay, so this is how you would define the conditional distribution x given y in the case of discrete random